Okay, now we can start. So last time we introduced all the basic notions of simplicial homology. We have functions on the vertices of a complex and flows on the edges, and given a flow like this, its boundary was the boundary of the flow, and given a function on the vertices, its boundary was the sum over all vertices. This is the zeros boundary, the first boundary, and the second boundary was for a flow like this. And for a triangle flow going like this, the boundary was this edge flow, and we had maps going in the other directions, the co-boundary, which takes a function on vertices to the differences. So this is 3 and 2, and taking a triangle, so to the sum. How do I? Okay, so this is the complex of homology and cohomology, and we had some important spaces. So this is the second boundary. This is the second co-boundary, the first co-boundary, and the first boundary, which takes a constant to the constant function.
Makes sense to call them derivatives and integrals, no?
Yes, or also differentials. Yeah, they have lots of names. Yes, these are usually called the differentials. Derivative would be the other way. No, it would also be derivative, yeah.
Derivative is right and integrals are left, and you're adding things.
Okay, but I won't move to this. And we had the splitting. So RV splits as the image of del 0 star with direct sum with the kernel of del 0, which is the const. These are the constant times sum 0, functions of sum 0. And the analog splits in one dimension higher, so 1. This was Kirchhoff, and this was exact. So I remind you, Kirchhoff means that what comes in goes out in every vertex, and exact means that the integral over any closed path is 0. So this is the analog splitting to what we know from graphs of constant and sum 0. And we had the Laplacian, which was Now for a flow, for an edge flow, what it gives to an edge is the original value times the degree. And here the degree is the number of triangles it contains, minus the sum over neighboring edge, where neighboring here is the following. The directed edge E is neighbors with this directed edge and with this directed edge. So these are the two neighbors of this E. Yes?
The way to understand, so these are obvious analogies, but is there a way to see better? So on the right, the kernel and the kernel are sum zero. So, this is locally sum zero, right? Sum zero at every vertex.
Mm-hmm.
Above you, it's just, you don't have, there's just like one vertex, so it's sum zero. Here it's locally sum zero. That's a key one.
Yes.
Is there a way to see in what way the exact analog of the function?
That it's what?
Some locally.
It's not a local condition, because to know that the function is constant. No, also to see that the function is constant, it's not something you can check locally, and also to go over cycles. And it is what comes from one dimension below. So the constant is what comes from the scalars. The scalars goes to constant function on the vertices, and one dimension higher function on vertices go to exact flows. So these are the ones which are induced as gradients of one dimension lower. This is why they're, but yeah, I don't have more than.
Yeah, there's no more intuition than that.
No, y is exact and constant. The
Why
same.
do they look similar? I understand why the right hand side. Why they
So
look similar.
from the topology point of view, what we're doing is looking at, looking at copies of spheres. So in the upper one, we look at copy of the 0 sphere, and in the lower one at the 1 sphere. So the 0 sphere is all the 2 points. It's all the x's of norm 1 in R1, and here all the x's of norm 1 in R2. So this is a circle, and these are 2 points, and we integrate along. Here we look at whether the value at the 2 point is the same, and here we go over the cycle and look. So, but it's again saying the same thing in a different way. But this is also a little misleading, because when you go to higher, it's true that in the second level, I want, if I go over spheres, I want the integral of the triangle to vanish, but now I have also toruses, I have more manifolds in higher dimensions. So, and I want also them. So this is only part of the picture. Okay, so a few things to notice here. This sum, it's not, you don't see it, but here there are 2 deg E summons, because every triangle, right, this is the number of triangle containing E. And for every triangle containing E, I have 2 edges coming from this triangle. It seems very technical, but it causes a lot of problem. Most of the things that we understand how to do in graphs and we can't take to high dimensions is because of this. That this does not, this is bigger somehow than this. Okay, and like we said, the interesting spectrum of the graph is the spectrum of the Laplacian restricted to the Kirchhoff. So why Kirchhoff? Because this is the orthogonal complement of the exact function. Now, the exact functions are the one induced from vertices, and then when I do the Laplacian, I didn't write it, but the Laplacian is going from vertices to triangles, and then from vertices to triangles, and then back. So everything which comes from vertices, when I take it to triangles, it's 0. Right? If I take twice the derivative, it's 0. So this is the the trivial part of the spectrum. Like in the graph Laplacian, everything which comes from constant, the constant functions are the trivial zero of the Laplacian. So the spectrum on the exact is 0, and it's not interesting, but the Kirchhoff is interesting. And we said that 0 is in the kernel, is in the spectrum, in the non-trivial spectrum, if and only if the homology is non-trivial. So there are holes. Okay, so that's a reminder. And the second thing we did last time was showing that we have a Chigger inequality, that this spectral, so lambda, which is the minimal value in the spectrum, bounds from below the Chigger constant, which was going over all partitions ABC and dividing by the size, normalizing by the number of vertices. And here, ABC is a partition. So this was bounded from below by the spectral gap, and this we showed. Now what I will show you is the mixing lemma. So now we assume that the spectrum is not only far from 0. Here we wanted the spectrum to be far from 0, but now we want it also to be bounded from the other side. So we assume it's contained in some strip, let's say k minus epsilon, k plus epsilon. And think about k as k can be any value, but we want epsilon to be small comparing to k.
I have a question. Do we have any lower bound on how small lambda can be given? You know, like an analog analog.
Okay, so I will get to these things, yes. That's a good question. That's a thing to say. Okay, so here we have a spectrum. The spectrum is concentrated around some k. And what I want to show is that now for any disjoint ABC, the number of triangles deviates from k over ABC, and so now this will be A, B, C. The deviation is bounded by epsilon times so. ABC 2/3, and for graphs you know most of you probably know the same statement with the edges between two sets A and B. Here it would be KABN, and here it would be epsilon times AB to the 1/2. That's the expander mixing lemma, the classical one. And okay. It works for any k and any epsilon, but for if you give bad values, then your bound here will not be interesting. It will tell you that the number of triangles is non-negative or things like this.
Epsilon is like 10k.
Yeah, 10k would be, yeah. We want epsilon, I mean, what you want usually is epsilon to be something like square root of k. This is what we aim to.
Don't you have a trivial bound that the spectrum is between
Yeah, so
average degree or something, and you always have some bound, right? Like 10 times the degree.
3. Yeah, 3 times the maximal degree.
K is like the average degree, and epsilon is like 2k. This will always.
It's true, but it won't tell you.
The bound is true, but it's not.
The bound is true, but it won't tell. This won't tell you anything.
Why would it tell you anything if epsilon is like a constant and AB and C are large?
Oh, you say from the other side that it will bound from above? The number of triangles? I have to work it out, but
It's a lower order term. It's like a smaller power of n, right? So it will have very strong concentration.
Ah, you say already.
K, this can have 0 in it.
It's what?
Epsilon is K, this can have 0 in it, the spectrum.
Yeah, definitely.
If you have 0 in the spectrum, you don't expect to have split spectrum.
No.
No, you don't have, right? So
No.
So this can't hold for large epsilon.
No, it holds.
But no, if epsilon is K, K is a constant.
Mm-hmm.
The error term
Mm-hmm.
is still very small compared to the it gives us some good estimate.
Why? This is A, B, C divided by n. You want K and epsilon to be the same side. And here it's A, B, C to the 2/3. So it's something, let's say, they're all at the same sign. So this is like n square. And this is also n square. Yeah, I don't get. Yeah, usually, I think you usually get something interesting when they are linear with n. Okay. And again, this works for higher dimensional complexes, but I'll do it for triangle complexes where we can see everything graphically. So we have A, B, C. And now we look at the form.
Does the 2/3 depend on the dimension or not?
yeah.
Yes, yes, yeah. It will be 3/4 and 4/5. Yeah. Okay, so and now we also have vertices outside and vertices inside, and we have edges, we have triangles, and we look at the form which gives 1 to all the edges going from A to B. So let's call this one AB, this form. And in a different color, let's put the form 1AC. And what I want to look at is the inner product between 1AB and the degree operator minus the Laplacian 1AC. Okay, so the degree I just
Sometimes the degree from the Laplacian. In the graph case, it's already
Is
encoded
there-
in the Laplacian. In the graph case, you take this by linear form with
I think in graph usually people just look at regular graph and then the degree is just a scalar. But
sorry, but yeah, but if it was regular, then the degree shouldn't be that. Let's assume the complex.
if it was
So the adjacency.
so actually it was you can
Sorry, good. This is the
yeah. Oh, okay.
Yeah, we want the adjacency.
Exactly.
We just want the term.
So yeah,
adjacency.
I was just going to say. So let's call the first adjacency operator give to an edge the sum over the neighbors. So this is really the adjacency. The adjacency of directed edges. And so what happens here? I take one AC and I move it to neighbors. So the adjacency operators take the value from E and put it on, or the other way, it takes the values from all the neighbors and put it on E, but it's symmetric. So it also takes the value from E and put it on all their neighbors. So what I will get here is that if I write in pink the differential of the neighboring operator of 1AC, it means that for any triangle going from AC, now I have one like this and one like this. So for any triangle going out of AC, I get this. Some of these edges go from A to B. Some of them don't. But then I take the inner product with the form 1AB, which is supported on edges going from A to B. So these are the ones which interest me. All the other will vanish in the inner product. And since I still get 1 for every edge, this is exactly what I get here is the number of edges going from A to B who have a neighbor going from A to C. So this is number of edges going from A to B such that there exists a neighbor going from A to C. And this is the number of triangles. every triangle give you a pair of neighbors.
This is analogous completely to what happened in the graph.
Yes, this is exactly. And now, actually, I don't need this degree, so because 1AB and 1AC are supported on different edges. You don't have an edge going from A to C and from A to B. So it means that when I look at the degree, I see this is 0, right? This is just multiplies all this by the degrees, and then I take inner product with something disjoint, it's 0. So I really can look only at the Laplacian. But it's not what I want to do. I want to look at the shifted Laplacian. So I want to go to AB and K. I just shift by K. And again, it's by the same reasoning. I take K times all the edges, this form times this, it's still 0. So this is like, instead of the degree, I look at the average degree, really. Somehow, I couldn't avoid it. But it's still the same. Now, what we know is the spectrum of this operator on the Kirchhoff forms is concentrated. So let's split it. So let's write let's split 1 AC to the Kirchhoff part and the exact part. So this is in the kernel of the downgoing Laplacian, and this is in the image of what's coming from vertices. Okay, so and this you know that it's in the kernel of delta 2 star. If I take it one dimension higher, it vanishes, and this is the kernel of the Laplacian. So this part vanishes in the Laplacian. So we have 1 AB. Okay, now I need, yeah. For this I need the, yeah, okay. 1 AB, and here K minus delta 1. Okay, let's still write it.
You still have here the complete skeleton of
I still have here, yes. Yes, if I don't have, there's much more work. What do I get?
Then you won't get this ABC.
No, no, it will involve things happening in lower dimensions. So 1 AB, 1 AC Kirchhoff, and 1 AB K minus delta 1. Exact. Okay, and what do we know? The exact part is in the kernel of the Laplacian. So I can just remove this and stay with K. And the Kirchhoff part, okay. The Kirchhoff part, what I know is that the Laplacian is very concentrated in the spectrum over the Kirchhoff. And now notice that
The norm of K minus delta 1 is at 1 epsilon. So whatever you do, you get epsilon.
yeah, but you still need to say something, one more thing, which is this is still Kirchhoff. Right, K times this Kirchhoff form is Kirchhoff, and the Laplacian takes everything to Kirchhoff because it goes one dimension higher and then lower. So if you go one dimension lower, you vanish. So this is still Kirchhoff, and it means that I can multiply here by the Kirchhoff. No, because it's an orthogonal projection. So this also splits for the Kirchhoff part and the exact part, and I can take only the Kirchhoff part because this is in Kirchhoff. Okay, so now let's call these This will be A and B. So A is really easy. Like you said, Avi, this is bounded from below by the norms. And this operator on this space is bounded, its norm is bounded by epsilon. And if you want to work hard, you can give a real estimate to this, but I'm just going to bound it by the original sizes. This is a projection, so it only lowers the norm. And now what is 1AB? So it's 1 over all the edges going from A to B. So this is square root of sum over E 1AB. So this is square root of AB.
So what is the rule to take the Kirchhoff out of 1AB if you're estimating it maybe
Theoretically, this could, if this would go out of the Kirchhoff, then I would also have to add the exact part of this. So actually, to say that this has a spectrum on the Kirchhoff already says that it sends Kirchhoff to Kirchhoff. So actually, it was implied in the beginning when I said that the spectrum is the non-trivial spectrum, the spectrum restricted to the Kirchhoff. I already said that it sends Kirchhoff to Kirchhoff. So I don't need to do this again. You're right. OK, so this is the norm. And so this is we get here A, B, C.
You have to do it for all the weights.
Yeah, so just to make the sentence symmetric, I'll do it for all the combination and then take the geometric mean. But actually, this is, if one of them is bigger than you want to use, you don't want to use that one. Yes. So this is the error term. This is the easier part to understand. Not the error term now. This is going to be this part. And to see this, I'm going to introduce another operator. So this is the lower Laplacian. I'll draw it as an upside-down Laplacian. It's going down and then up. So the lower Laplacian on edges would be going down from edges to vertices and going back up. So this means that I take a flow on edges, send it to its derivative, to its boundary, and then back to edges. So you know this in dimension 0. What happened in dimension 0? I take a function on the vertices. I take it to the scalars. Now the boundary here is you remember the function which takes the sum. And here this is the adjoint. So you compose them, you get the all one matrix. So this should be familiar to people from graph theory. You see this a lot, but here it's how it turns up in the general context. And so why do I need this? Because now we need to understand 1AB. And here we have, OK, let's take K outside. And here we have the projection. Now I write the orthogonal projection on the Kirchhoff of 1AC. What I claim is that to understand the orthogonal projection, I'm going to use the lower Laplacian. Now you know this from graphs. If you take a function on the vertices and you multiply it by the all one function, you get a constant. Is this an orthogonal projection on the constant function? No, because I blew up the norm. What I need is to subtract from f a function of some 0. So it means that I need to keep the sum of f constant, and this means that I need to normalize. But this is the projection onto sum 0. So the same happens in general dimensions. If the skeleton is complete. So let's prove this lemma. 1n over delta 1 is the projection on the Kirchhoff. And really to understand what happens, a lot of time this is in all this work usually to understand how the splitting to Kirchhoff and exact look in higher dimension is the challenge. So in this case, we get, this is something which is pretty mysterious, but now we turn it to a combinatorial problem with the Laplacian. And most of the time that I know to say something, it's because it's related to the lower Laplacian.
So here, what is L?
Number of vertices. Okay, so for the proof, so first of all, yes, this is still for a complete skeleton. So first of all, the exact go to 0, right? Because this is delta 1 star, delta 1, and the exact is what's coming from okay, yes. We want the exact. So everything I said, but the opposite. So the exact, and this take the Kirchhoff to 0. Because the Kirchhoff is what's coming from one dimension above, no, it's not coming from one dimension above, sorry. But it's Kirchhoff. Okay, so by definition, this is 0. Kirchhoff is its boundary is 0, so the Laplacian takes everything to 0. Now, the image of the lower Laplacian, so this is that one, not that one. This is the image of, this is always true. If I have an operator between in a product space and I take the composition with the dual, it's the second one. You remember for the kernel, we had the kernel is the kernel of the first one. So this is the same trick. So I already understand, and this is the exact. So it means that if I look now at the decomposition to Kirchhoff and exact, I already know here that it sends Kirchhoff to 0, and the image is only in the exact, so it means that this is also 0. So I need to understand what happens here. And here the rank is full because the image is the entire exact. So I want to understand the spectrum. And the spectrum of delta 1 restricted to the exact, because the exact is exactly the orthogonal complement of the kernel, right? The kernel is the kernel of del 1, which is, by definition, the Kirchhoff, and the complement is the exact. This means that this is just a non-zero spectrum. Okay, stop me if I'm going fast or some of.
Trying to show that all the pairs in the spectrum are the same.
The what?
Trying to show that all the spectrum is the same.
Yeah. And okay, what is this? It's del 1 star, del 1. And here is another trick for linear algebra. The non-zero spectrum of a matrix times its transpose is the same as the other way around. So this is like del 1 star minus 0. So when you take T transpose T and T transpose, the difference in the spectrum is only in the zeros. You can see this from singular value decomposition, or you can work it more explicitly, but with more work. And this is the zero-dimensional upper Laplacian. So, right, we don't have the picture anymore, but instead of going from edges to vertices and back, we're going from vertices to edges and back, which is the graph Laplacian. So this is the non-zero spectrum of complete graph, non-zero Laplace spectrum of a complete graph. And
of whatever underlying graph is there if you had a different skeleton.
yes, so I didn't use until now here the fact that the graph is complete, but here I use it to say, okay, the non-zero Laplace spectrum of a complete graph has a single value n, and I leave it as an exercise. If you've never done it, it's very easy. And like Avi says, if the underlying graph is not the complete graph, but I also understand its spectrum very well, so let's say it's very concentrated, then I will understand. It will tell me that the lower Laplacian is not exactly projection, but it's close to being projection. I can work with that. This is how you go to the non-complete skeleton parts.
So if, for example, the underlying skeleton is an expander, you would get a similar.
Yeah, yes, exactly. Yeah, I need, this is what I know to do. I know how to work when the lower dimensional skeleton is an expander from both sides, not like only Chigger content. I need from both sides. Then I can work similarly. Okay, so what did we get in total? We got that the spectrum over the exact is only n, and it kills the Kirchhoff. So this proved the lemma. It means that it's projection over the exact, but multiplying by n. So this is k over n, 1ab, lower Laplacian. And now I can do the usual trick. This is k over n, and now this will be delta. So this goes from. So now I take the AB form and I look at the differential. So its differential give to any vertex, say here, what do I get here? For all the edges entering here, I get 1 from all of them. So this is just A. Right, I still assume a complete skeleton. And all the vertices here gets minus B from this. And this is the same. It will get C here and minus C here and A there. And then I go over all the vertices and multiply this with this. So outside of A, everything will vanish. And in A, I'll get BC. So in total, it's KABC over N. And again, if it's not a complete skeleton, but the skeleton is an expander, then I can estimate this size more or less.
Then you'll have error terms, one from the lower Laplacian, one from the upper Laplacian.
Exactly. So I don't think I'll show today what happened in the mixing. There are some details, but I think you see the general picture.
Yeah, but which is worse? So which of the two
What?
error are they unrelated? I mean, suppose you had, you use the same epsilon here and
They sum. They really sum.
They sum, but they have an effect. What do you mean they sum?
So if you look at the
here the epsilon would be added to the main term, right?
at the end, what I will get is something like K0, K1. So this is the average degree in dimension 0, average degree in dimension 1. And here it will be K. This will be the error. So I mean, they really sum in the sense that the correct scale to look at the epsilon is compared to k, so the other way. Yes, so
But this would be multiplied by ABC to the 2/3.
yeah.
I see.
And
They produce the same, units of error.
yes. And here then you'll need there will be some constants here. But it only depends on the dimension.
I don't understand because it seems like it would, this error from the expander will come in this calculation only, right? In the B. I know. So the A part gave some error, ABC to the 2/3. The lower part, you just get, because the degree is not constant, this spectrum is plus minus, let's say, delta. So there'll be a delta, so there'll be, I think.
I use it at least twice. Once here to understand these, to understand this, but also here for this lemma I also need the complete skeleton.
Yeah.
This plus delta something.
Yeah, exactly. So I'm asking whether delta will be multiplied by units like ABC over n or by units like ABC to the 2/3. It's not the same.
So
What will be the units in which the error from the expander is multiplied?
no, you're right. It's
ABC.
no, you're right. I'm cheating. It's yeah. Yes, it's not ABC to the 2/3. It's more complicated. And at some point I stopped using ABC. I just took the biggest one of them, and then I can bound in terms of the bigger one.
I think in the non-complete skeleton, you also have to look at sets that are linear in n.
Yeah, but I think also
No,
here.
it doesn't matter. There is an error term.
No, but I think if you look at sets that are linear in n, both error terms are
But
the
also
same.
here, if k is constant, you need to look.
Yeah, also here you need.
If k is constant, you get nothing for some linear ABC.
You're right. I'm cheating here a little bit, but it's not much worse. I think I still get something like.
I'm just, well, it doesn't matter. We can talk about it.
Okay. So I'll what?
In the regular expanders, you get something like this also for not just for partitions, just for any two sets, even if they're small sets.
Yeah. If
The expander mixing lemma for graphs, it's not just for partitions.
yes. Also here.
Any two sets.
Yes.
No, here you needed the.
No.
But here it doesn't work if the sets are too small, right? It's only for like linear.
But it's also in graphs.
No, but in graphs you can go all the way to square root 10.
Oh yeah. I think you can go a little below linear, but not. I mean, so it won't be square root. It will be 2/3 or something like this.
Because what you wrote here fails breaks for linear, right? That's the best.
No, I don't think so.
All the sets are n to the 1 minus epsilon.
Really? We'll think about it later. No, I think you can go a little below.
Maybe to tell us if we know concept as well is
Okay. Okay, so what I wanted to do today is show you the Chigger with non-complete skeleton, and also to tell you other things like Alon-Bopana. So I think I'll start with other things, and at the end, if we'll have time, I'll do the Chigger with non-complete skeleton. Okay, so Alon-Bopana. So if is an infinite family of k regular graphs, then the lim inf of the spectral of the minimal eigen, this is the minimal non-trivial eigenvalue of the Laplace operator, is at most 2 root k minus 1, right? Okay. 2 root k minus 1. So it means that if you're trying to construct k regular graphs with large spectral gaps, eventually you can't build an so it means that if I want all of them to be 2 root k minus 1 plus any epsilon, I can't do it. For any epsilon, there are only finitely many with lambda at most this. So eventually I will get closer and closer here. And greater or equal? No, it's
I mean, take this connected graph and they will all be zero.
Ramanujan graph has a graph.
no connected graph. This is the non-trivial spectrum.
It is a non-trivial spectrum and it cannot be lower than this. Some other graphs have this property.
It's a Laplacian.
Yeah, but this is still correct. You're saying I need to reverse this? I can have an infinite family which is.
This is what is lambda of Ti?
It's the
Epsilon with the wrong sign. Then you want to write k minus. So you want to write at most k minus.
oh, okay. Yeah, thank you. Well, I asked you about this. You said it was okay. Yeah, it's a you saw the adjacency.
Yeah.
Okay. Yeah, so k minus 2, k minus 1. You can't go, you can't stay above this value for infinitely many graphs. So what happens for complexes? So I'm going to get here, but I want to start with something else, which is this process of random walk. So we had the notion of neighboring vertices, so why not look at the random walk, neighboring edges? So let's say I start with this edge, and I move to this edge with some probability, to this directed edge, and to this edge with some probability.
This edge may be in many triangles, so you first pick a random neighboring triangle and then do this.
Okay, yeah, so let's take a more interesting example. So I have here now 4 options. I look at all the neighboring triangles, move to one of them to the edge in the correct orientation. And I'm going to add a probability to remain in place. So I also remaining in place. So this, I'm going to be pretty drastic. This will be with probability half, and all of these 1/8. So this looks like a natural generalization of random walk from graph to higher dimension, because we have this notion of neighboring directed edges. So how do I understand from this walk the complex? What do I understand from a graph by the random walk? So the most basic thing is connectedness. If you have a graph, if it's connected, then the random walk will get anywhere. If it's not connected, then not. So let's say it in terms of the Simplicial theory. If I take the probability starting from some vertex v0 to be n. So, okay, let's try this. The probability of going from v0 to v in n steps. And let's write the distribution at infinity. Okay, so this is the steady state distribution starting from v0. Then in graphs, p v0 infinity is constant, but I will say that it is in yes. Yeah, for regular graphs. Yeah. Otherwise, you want to look at the normalized Laplacian. And you can do the same in higher dimension, but let's say with regular for now. So this is going to be constant if and only if the graph is connected. So I want something like this in higher dimension. I want to see the homology of the complex by this random walk. So this is, I think if you got this question as a riddle, just construct a stochastic process which tell you if you walk around locally and you're trying to understand by the behavior at infinity if there is some hole somewhere that you're going around it. I think it's very, I don't think you could reach the, I don't see how I would, but it's true and it's trivial. It's when you take everything we did, we take all this Simplicial Hodge theory, and repeat this proof, you get an answer. And the answer is the following. So let's look at probability going from some edge. So this is the probability of starting from some directed edge and in n steps going to a different edge. And I don't want to work. This will give me some function on all the directed edges. But I don't know how to work with function. I know how to work with forms, with flows. So I'm going to make this a flow by anti-symmetrizing. So I'm going to subtract the probability of getting to the same edge, but in the opposite direction. So now this is a flow, right? If I have some value here, then the value in the opposite direction will just flip this. I'll get the minus. So I call this the expectation at time n at e. Now, okay, let's. So this is a directed edge. So the expectation at uv is the probability to reach uv minus the probability to reach vu. And I think expectation, it's because this is, if you evaluate at time n, this is the expectation of what you get. You have some probability to reaching here and minus at the other direction. This is a flow, yes. So the expectation, so expectation at times n starting from some e0 is a flow on the graph. And I can look at expectation at time infinity, which is the limit. And what do I get? So I have some graph. I have some complex. Take this complex. And I look at the probability starting from, now for every edge I have two directions. And I started somewhere, and I look at the probability to end up here minus the probability to end up here after n steps. It will get arbitrary close, right? Because right, I have actually 6 states, and I'm going between all of them, and I can reach from all of them. So it's like a connected graph. So the probability at times infinity is constant.
All of them from all of them because of this definition. Because otherwise there will be two disconnected cycles, clockwise and anti-clockwise.
No. I can always. No, that's a good thing. I need to show this. So I can always go from this here. Then in one step I'm here, and then in other steps I'm back. Sorry, here with the opposite direction. In two.
How did you do the first step?
I go like this. I go like this, like this, and like this.
Okay, so
Yeah, I can always flip. In three steps, I can always flip my direction. It's not, it doesn't preserve. So it means that, yeah, in 3 steps, I can get from this vertex to this vertex. If you think on the 6 vertex graph, it means that at times infinity, my probability of being here and here is the same. This is really, you can really construct the graph I'm walking along with something like this. You get from everywhere to everywhere. So this is 0. This is not very interesting. But the thing is that the decay here is well understood. This is 3 quarter to the n. It decays geometrically, and this is the rate of decay of the expectation flow. And it means that I need to, I would say, blow it up to see what really happened. So what I'm going to look is 4/3 n times the expectation times n, and I look at the value at infinity. So this is what I really want to understand. I need to, I know that they're going to be, that I get to them in the same amount of probability at infinity, but now I want to see the small differences. So, so 4/3 is for triangle complex with the probability of half to remain in place. If you go high dimension, this will change, and if you change the probability to remain in place, it will be the same. But until now, I haven't said anything interesting. The thing is that now you can understand the homology. So this flow at infinity is exact if and only if, for any starting point, if and only if x is, the first homology is 0. So it's like the probability of a random walking graph is exact if and only if the graph is connected. So now this is the first. If the first homology is trivial, then I get for any starting point, I'll converge to an exact forms. And the way I think about it is this. So here's a here's a complex, and let's say I have a hole here. So this is outside. This is not in the complex. All the others are. So this has a non-trivial homology. When I have non-trivial homology, it means that I can orient things around the hole. So here I've oriented the edges around the hole. And if I walk in this, if I start walking like this, I need also this. Let's say I started here. At the next steps, either I'm going here, which is still in the correct direction, or I'm going here, which is still in the correct direction. Here, it's the wrong one, and here it's the wrong one, and I have a probability to stay in place. So in total, my chance of staying in the orientation I started with is bigger than flipping the orientation. But it's not like graphs when if I start in one connected component, I'm definitely staying in that connected component. If I pick a hole and I start with some orientation with respect to the hole, I have a chance of losing it in the next step even. But my chance of remaining in the correct orientation is always bigger. And I'm trying to amplify this chance a long time. And if I do this, I really get the results. At the end, I can convert to something like this. It means that the graph is not exact. This is like this form with a hole in it, it's not exact. If I take this integral, it's not 0, even though it's a closed integral. Take 1 plus 1 plus 1. So it's a very shaky intuition. What really happens here is just taking the proof from graphs and seeing what you need to change for it to work in complexes. What? Yeah. Yeah, you don't need to normalize. And you get the same thing. But there are many weird things. For example, I need here this for every epsilon f is in epsilon 0. In graphs, you can start with any point and start from it and understand the homology. Here, you really need to take all the starting point. There could be some starting edge for which you'll converge in infinity to an exact form, even though you have non-trivial homology. You need to try all of them to understand. Okay, so how is this related to Alon-Bopana? Basically,
This number comes from the
Mm-hmm.
What is the universal cover of this system?
So yes, this will be too optimistic, but it's along along these lines. So
Well, why is that too optimistic?
what?
Why is that too optimistic?
Because there is not such a thing like the universal cover of all complexes of constant degree. They have different covers, and I don't know what to do. I mean, they can look in different ways. I don't have something global like all the complexes of constant degree k are bounded by this and this because they don't have a common universal cover. What I can say is this. So if
Because the buildings form naturally.
not really, because you only have them for prime degrees, for example. Even for graphs, you can only understand some of the graph as quotients of buildings.
Along Bopana, you can understand.
Along Bopana, yes, but not from building theory. Right. Okay, so what I want to say is this. If a sequence of graph converges to a graph, then for any value in the spectrum of the Laplacian, okay, let's take triangle complexes.
Now
So
graph is a weighted graph or what?
no,
What
sorry,
is it?
complex.
Convergent.
Okay, so this I need to explain this in a moment. What is convergent? If a sequence of, let's say, triangle complex converges to some complex, then for any value in the spectrum of the n complex, there exists a sequence which converges to this value. And what here is convergence? X and converge to x mean that there exists some edge En in Xn and E in X such that, let's say, the balls of radius n in Xn around En is the same as the ball in radius n around X. So it means that I look at my complexes, I choose some base point,
They are
and
infinite now.
what?
They are infinite now. X.
No,
You're doing it ball by ball.
I didn't say that any one of them is infinite, but
The complexes are not infinite.
they can. It's not very interested if they're all finite, because right after some time the balls will just tell me the entire thing. But it's more interesting when X is infinite in X and finite, but they can also be infinite.
This is much weaker than what's with Benjamin Schramm.
This is stronger than Benjamin Schramm.
So you need most points. You're saying for every, it's locally looking like.
Oh yeah, it's weaker. So,
you
but
just
what
need some neighborhood in which it's looking like this.
exactly? Yeah, it's strong in the sense that this is enough for me. So this,
Weaker condition.
you're right. Okay, so for example,
Because in the Benjamini Schramm, you would have convergence of the actual densities of the spectrum rather than just subsets.
other than just points.
That's one of the points of the emotion.
Okay, so for example, let's look at this sequence. So this is a sequence of graphs, but you can do the same thing for graphs. And this sequence of graph converges to what? Infinite line starting somewhere, but also the infinite double line. So the limit here is not unique. If I chose these, I'd have this choice of a base point. If I chose this base point, then the convergence is to the one-sided. If I chose this base point, then I would converge to this. So it gives me a freedom. But it means that the statement is true for both of them. For the spectrum of the two-sided infinite line or the one-sided line, for both of them, these have eigenvalue which converges to all the points in the spectrum, which I think is the same.
I think actually that's a good example of where the first graph, the bi-infinite thing is the Benjamini Schramm graph.
and this one is not.
Yeah, because most of them will apply.
Okay, so oh, and why is this related to the and the proof basically goes by looking at the walk. This is what I wanted to say. So for graphs, if I look at lambda, if I have an infinite graph and I look at the minimal spectrum of the L2 on L2 function, this is the limit of the probability to return to my starting point after n steps. So this is, I think, very standard, and it tells me that I can understand the spectrum by walks. And just starting from this, you can get this theorem for graphs, that if a sequence of graph is connecting to a graph, then the spectrum converges in this sense. And when you do the same thing with this process, you get this theorem for complexes. So basically, there is this walk, and then you have some magic box, which is called Boel functional calculus, and you get convergence. But I don't know that the spectrum is entirely. I mean, it can have isolated.
Doesn't matter. Bell's criteria is completely changed.
Okay.
Well, in fact, unbounded operators.
Okay, so this is very. What we actually did here, just to read a proof of due to Grigorchuk and Juk of the Alon-Bopana, and it really they use this machinery to start from random walks and get the Alon-Bopana theorem for graphs.
I'm not sure, so I don't know what this little box is. But I know how to prove the first statement. It's just a trace method, right? I mean,
No.
just expressing
No, not to prove this.
No, I understand.
To prove
what did you use?
this. This is the convergence of spectra. Why, if I have,
Okay,
yeah, this is to, and I think Peter has simpler way to prove it. And the thing is that these theorems, I think it took it some time before it was really understood what happened there, because Alon-Bopana had a very combinatorial argument, and then there was an argument. Yeah, but you also did something very combinatorial there, right?
We just use a tree. But the point, you have to be able to compute something. For this to be useful, you need the spectrum.
Not only this.
You use it now, you have to tell us how you can understand the spectrum of X.
That's true, but I think also to understand that you can do this for general graphs, not for regular ones. It took some time before. I mean, this is from '99, and I didn't see such a general form before that. But really, for any convergence, you get convergence of the eigenvalue.
I think Alon-Bopana is published on the media.
Yes. Because the proof that you wrote wasn't the one he thought of, and he wanted to have also his one in print. Okay, so what happens here is that the spectrum indeed converges, but Alon-Bopana is more than that, because it's the spectrum restricted to the non-trivial part. So if I have an infinite graph, and a sequence of graph converges to it, I want to say, and I want to say that for any point in this spectrum, there is a sequence of non-trivial eigenvalue which converges here. Now, So let's say lambda is the minimum spectrum of the Laplacian of the graph. The point is that if lambda is 0, then the spectrum of the Laplacian of this graph have a sequence of eigenvalues converging to this lambda. But maybe all of them are 0 and they're coming from the constant functions. But the eigenvalue 0 correspond to the constant function, right? And it can't be an isolated point. Lambda cannot be isolated, right? Because an infinite constant function is not in L2. But I'm using here, I'm skipping parts, but an isolated point in the spectrum corresponds to an eigenvalue. An eigenvalue 0, it means that it's in the kernel of the Laplacian, which means it's constant. It's a constant function on the graph, but the constant function on the graph is not in L2 for an infinite graph. So lambda cannot be isolated, which means that in the graph I have a sequence of eigenvalue converging to zeros. For each one of them, I can find a sequence of eigenvalues converging to that one, and then I take a diagonal sequence, and it converges to 0, and it's not in the 0 spectrum of these graphs. Okay, so this is also the argument from Grigorchuk-Zuk, but I can do it for in higher dimensions. So 0 can be isolated in the spectrum of the first Laplacian of an infinite complex. And we tried to bypass this for a long time, and at the end we gave up and constructed a counterexample. And it's the following. You start with this complex, two triangles around an edge, then you add another triangle anywhere, another one. It looks like a tree, yes. And this converges to some infinite complex. We like to think about it as some, you can construct it as some ideal tessellation of the hyperbolic plane. The spectrum here is an isolated value at 0 and everything from, I don't remember, 2 minus square root of 3, I think, to 3, something like this. And here the spectrum, all of these are contractible. So the first homology is trivial. It means that I don't have 0 in the non-trivial spectrum. So here the spectrum of all these is contained in this 2 minus square root of 3, let's say 3. So I don't get this 0 as an, so here I have a non-trivial 0 eigenvalue, which comes from only from the trivial eigenvalue. This theorem is still true, that I have a sequence of eigenvalues in the spectrum which converges to this eigenvalue, but nothing tells me that it's non-trivial, and it is trivial at the end.
Of course, you know that building symmetric spaces, discrete series, which are L2 isolated.
That they don't have isolated point? Oh.
L2 eigenfunction, you come back to both.
No, I didn't know that.
Only cohomology, not a function.
What? Okay, I think we should take a break at some point.
Yeah, so
But just to sum this,
yeah, where are you going? Sorry.
where I'm going is, first of all, we have, I was trying to say what we know in terms of Alon-Bopana. So since we don't have a universal cover of general complexes, we have this more general approach of taking complexes converging somewhere, because a sequence of k-regular graph doesn't necessarily converge to the infinite k tree, but some subsequence converges to some infinite k-regular graph, which is covered by the k-regular tree, so you can still work with that. But here we don't have something like this. So we start with some infinite complex, which we converge to, and then we can say that all the spectral values of the complexes along the way converge there. but we still have this problem of 0. If 0 is an isolated point in the spectrum of the infinite complex, it could be coming from non-trivial 1.
But for an alone Bofana, which is where you get,
Yeah, this is
you have to identify somehow these limits that you do.
what to do
As we remarked earlier, that in the case
to
of
compute the spectrum.
the graph, the universal covers a tree, and that is responsible for alone Bofana. Here you're saying that you don't know what the universal object is.
Yes.
So you have to say something about the potential universal object.
So we had one idea which was just construct these 3 analogues in higher dimension, start with anything tetrahedral, and then add to all the faces k tetrahedral, and so on, just build a 3-dimensional tree, k regular 3-dimensional tree like this. For this, we can compute the spectrum of all of these, and they look very nice. They generalize trees, but also have some phenomena like isolated eigenvalues. And for trees, when k grow higher, the spectrum shrinks. In these, the spectrum actually expands until k equals the dimension, and then it shrinks back. So there's interesting things here, but basically it's look pretty much the same. And the other infinite object which is interesting to work on is buildings. So
Exactly. I repeat Avi's question. Do you have the analog of alone Bofana, some lower bound that's universal? So that
it means that if you have an infinite family of a quotient of one of these objects, then I have a bound for this family. But there's no like universal.
No, for k regular.
No, not something like
triangle
this.
complex.
No.
So, but all this machinery, if you just wanted some non-trivial upper bound, let's say in the Alon Bofana case, you don't need Alon Bofana, right? The baby version of Alon Bofana would give you, instead of 2 square root k minus 1, would give maybe square root k over 2, so some weaker bound. And for this, you just need to square the graph.
No, this I don't know.
It's one-line calculation. You do the trace method, but you're all there, but take n equals 2. So just ask what's the probability that you return to the origin after a walk of length 2. And this already gives a bound, which is, square root k over 2 or something like that. So you can get something, some bounds much more trivially, and you did try it.
I didn't know of this, so it seems interesting, yeah. Because we don't have anything which is locally. At some point we did conjecture that if all the degrees are bounded by k, it should be bounded from this, but it's only by looking at examples. So I'll be happy to hear it. And and the other thing is that about Benjamin Shram is that this captures a lot more, because all the 3 examples in Benjamin Shram, the reason we didn't like it is that, for example, this doesn't converge to the 4 regular trees, and we want.
Alon Bofana is quite different to Benjamin Shram.
Yeah.
Benjamin Shram is a much stronger condition, and then the spectrum converges in a much
So the spectral measure.
strong way, which is exactly what Alon Bofana is even in essence.
So and it could also happen that in Benjamin Shram we don't have this problem with isolated eigenvalues.
Yeah, right.
Okay, so what I'll do in the, how much time do we have left?
Maybe taking a break, but doesn't make sense unless you want. Well, it's 12:30, so you
12:30.
can take a break, and or you can continue, or maybe less, or whatever you like. You are the boss.
I'm okay, but I think people are probably exhausted.
We've had many 2 and
Okay,
2.5 hours.
Okay.
Continuous, so it's
Avi, close your ears for a moment, and let's hear what other people.
Let's take a short break.
Okay, let's take 5 minutes. Good. Ramanujan complexes. So, okay, first of all, we had this Alon Bofana bound for graphs, and okay, let's start with Lubotsky, Phillips, and Sarnak in 86, constructed for k equals p plus 1. For every k equals p plus 1, or I think only if p is 1 or 3 modulo 4, there exists an infinitely many K regular graphs with which beat the Lombopana bound. So the Lombopana tells us that this is the optimal you can get. If you want infinitely many K-regular graphs, eventually you get arbitrarily closed here, but it's not clear at all if you can get arbitrarily closed. And they showed it for p plus 1, and then Morgenstern did it for p to some power plus 1, and it's still open for general p. Yes. Okay. So yeah, you're right. In this formulation, it's not open. So I'll say it. So it's Spielmann. Margulis. I don't know. It's in Russian. So I heard about it, but I don't know what exactly.
They always, yeah.
The first is in English.
But you know, someone in Moscow now stating it as Margulis and forgetting about Lobotsky. So.
Maybe somebody is commenting that also.
So Spielmann, Marcus, and Srinivasova in 13 did this for any K. So the question is, can you have? But it's even more than this. I want the even more interesting is have the entire spectrum inside K minus 2 square root and K plus. Yes. So this is still open in the general case. So they have it. The Lubotsky, Philip, Sarnak have this, and they still don't have it. The most general theorem. So the construction of Lubotsky, Philip, Sarnak uses what is called the Ramanujan conjectures. So,
sorry, what's the result in the 2013 paper?
of who?
What's the exact result in the 2013?
So they showed for any K there's infinitely many complexes with this, but they could have also here 2K.
Completely different construction.
Actually, they have here 2K. Yes, and it's the first construction which is not.
We use a Riemann hypothesis. They use Lie X. They're very similar looking theorems. It's quite standard.
And so the graphs with spectrum inside this strip. Okay, I'll call this strip this interval I are called Ramanujan graphs. I don't think I said it in any point, but this is the spectrum, the L2 spectrum of the K regular tree. I think I should have said it in the previous hour. This is the reason that, yeah, you get from all this machinery the Lombopana bound, because the K regular graph converges to the K regular tree, basically, and this is the spectrum of the K regular tree. Okay, so I think it's around 2000, people started looking at higher dimension, at Ramanujan complexes. I don't think I will say what it is, but the idea is take the construction from Lubotsky, Phillips, and Sarnak and do the analog in one dimension higher. So they start with GL2 over the p-adic, and the analog is take GLD over the p-adic and imitate the construction. And since it was so successful in graphs, it's natural to look what happens in complexes. So there are several works of Lee and of Lubotsky, Samuel Vishne, and of Juk and several people looked at it, but all of them looked at operators acting on vertices. So, and we wanted to see what happens in higher dimensional simplicial Hodge theory. So at present, what we know is the following. The okay, this was very, so let's take X to be a Ramanujan triangle complex. And the spectrum of the zeroth Laplacian is, okay, and the degree of all the vertices here is about q squared. It's actually 2q squared plus q plus 1. The degree of edges is q plus 1. So it's completely regular. All the vertices have the same degree. All the edges have the same degree. And the spectrum of, let's call this k0 and k1. The spectrum of edges is between k0 minus 6k and k0 plus 6k. So this was q, sorry. Yes. So this is something like the root of k0. So this is very old, I think, at least in the paper of Lubotsky, Vishne, Samuels, it appears, and no, it's old. It's due to MacDonald, I think. Even it's something very ancient, and the spec and.
I think that's from Donald would be the other direction. But the spectrum small requires series something that the spectrum contains it.
You're right.
The other way around.
Yes. So
I'm not sure. You're going to say the spectrum.
there is one thing which is understanding the spectrum of the building, the universal object, the infinite object, that MacDonald, and how to construct finite complexes which give you the spectral properties of the infinite one. That's the that was the new part, which relies on the generalized Ramanujan conjecture for GLD proven by Laforgue. So this, but also they do the computation again there. So
it's not a complete skeleton.
no, it's not a complete skeleton because the degree is constant. So and the number of vertices will go to infinity. I have an infinite family. All of them degree.
So we said the degree of an edge is q plus 1, you mean it's either q plus 1 or 0.
The way
No.
you can visualize this very, very simply. I mean, the graph is big, but when you look around the neighborhood, let's say it has a k0 neighbor, this neighborhood looks like a projective plane. Okay, and you take all the triangles.
So what does it mean for the degree of e to the q plus 1 if there's some edges that are not in any...
Yeah, because if you look at the neighborhood.
No, edges which are not in the complex are not in the complex. If you want to say that they have degree
Oh,
Yeah, so
0, it's
that's
okay,
in
but
the skeleton.
I'm not thinking about them.
if you have one triangle, you have q plus 1.
If I have one edge, I have q plus 1 triangles around it. Yeah. And here the spectrum is something like k1 again minus something like square root of q, and here we were stuck for a long time. We tried to show that it's k1 plus root of q, and if we had that, we could proceed and do. I didn't show you, but in the expander mixing lemma, if all the spectra are concentrated in this manner, then
For us, we know exactly where the spectrum is.
so
So what's the problem? We know the smallest set in which the spectrum accumulates in the fashion you're describing in this case. And then that's what, from there you should be able, why are you saying you're struggling?
He's talking about the spectrum of delta 1.
Yeah, even delta 1.
I don't know.
So it follows from existing work, but we went to all the all the experts, and all of them told us, yeah, this can be computed from what we know, but no one could point out. So we went and computed it. Right?
Okay, but you got it.
Yeah. So what happens is
It's not like you didn't get it.
no, we have. But I think for general, what we do if we try to generalize this to arbitrary dimension will be at a loss.
Stick to triangle.
Yeah. So at the end, it's not concentrated. It has two strips, one of them something like this, and another one at 2. Okay. So the spectrum looks like this. We have 0, which corresponds to the Kirchhoff, and here we have around the degree lots of eigenvalue. Here we have around twice the degree eigenvalues, much less. Here there are most of the spectrum. Most of the spectrum is concentrated around the degree, and you can know that it will be like this because the average eigenvalue is also the trace of the Laplacian, which is the sum of the degrees. So you know that things should be concentrated around the degrees, but there are actually n minus 1 eigenvalues which are in this strip. And there is also this guy, which is 3K1.
So you cannot use the standard mixing lemma.
No. And also we have here 3K1. And so what happens here? We can't use the expander mixing lemma because we have these.
So just to clarify, the theorem is that the universal cover has this as its spectrum.
Yes.
And the construction puts the spectrum inside this set. It's the smallest
Yes.
possible set. Isn't it?
Yeah, so we have Laforgue is like a big black box which gives us complexes whose spectrum is like contained within the spectrum
And
of the.
it accumulates it, so it's no small.
Yes. So this is the mysterious part. We're trying to understand where these come from. They come from vertices because this is why the number is n minus 1. So it's like every vertex induces some weird eigenfunctions, this is what we're trying to understand now, where it comes from, how to bypass this and do something like a mixing lemma, like avoiding this eigenspace. This one is not very hard. This is a little like in a bipartite graph, you have the 2K eigenfunction, except that here you have it also if the complex is not tripartite. If this complex is tripartite, then the form which goes like this will be a form of eigenvalue 3K. But the thing is that here you can't get rid of this. So the buildings are tripartite. They have vertices come in 3 colors, and all the edges go between different colors and all the triangles. But even in quotients in which the colors are destroyed, you still have this eigenfunction. It's preserved, even though the coloring is not. But it's not hard to work in perpendicular to that one. This is the challenge we're working on now. But the thing is, we can do Chigger, even at this point, because this is far away from 0, and we have concentration here. So this is the last thing I wanted to show you. What? If it exists at all, I don't.
There's some set in the expander, in your expander mixing lemma, you don't know that it's satisfied by any.
Not with constant degree. If I take an infinite family and the degrees are logarithmic in the number of vertices, then yes, then the spectrum will also.
A random constant degree complex. You can only analyze log n degree for random ones.
Yeah, but also this, we did it only for complete skeleton. I guess it will behave similarly in that state. But there are really lots of good questions to work on here. I mean, we know pretty little. Okay, so we remember our Chigger was going over all the partitions and looking at the triangles going from A, B, C. Now, because I don't have a complete skeleton, it means that I can't look at this, right? Because I can just find two vertices which don't share an edge. Take A to be this, B this, C all the rest. And I'll never have a triangle going between these sets because there's no edge here. So it's not interesting to look at this. We need to change somehow the definition. And the same thing happens if we take these to be bigger. So if I still take A to be something like square root of n, for example, if I say that, okay, all the sets have to be at least square root, then I can still do something a bit similar. Just take any square root of n for A, then take B to be all the neighbors of A. Neighbors as a graph. So now all the edges going from A are going to B, and C all the rest. And still, if the degrees are constant, then at some point these will all be larger than the square root, and I'll still have 0 because all the edges leaving A go to B, so I can't have a triangle with A and C. So it means that you can't really do anything less than linear. So we need to change the definition. We say that this is the epsilon Chigger constant, and I want A, B, C to be at least epsilon n. So all the sets have to be linear. If you do less than this, then it's trivially 0. But for this, we can say that it behaves pseudo-randomly. So what we know is that for the Ramanujan triangle complexes, they have H epsilon x. So this would be q to the third n plus something which is q to the 2/2. And this is really the density you would expect in random. If you do the computation, what would you expect if everything would be pseudo-random? You take the number of triangle and say, okay, A times B times C times the probability to see every triangle. This is the probability. If not, it means that I've written this wrong, but it should be. So the thing is, it's true for every epsilon, but yeah, exactly. So the error, the dependence in q to the 2/2 will be dependent in epsilon. You get the constant coming from the epsilon. But it means for every epsilon for large enough q, this is interesting.
It means that you can go subconstant. Epsilon can be subconstant.
Oh.
Depending on way, okay.
In q, yeah. Okay, so this is what I want to show. And you remember last time we looked at this form.
So this should follow from what's on the upper board, right?
Yes, and then
Spectra that you have over there.
so what I'm going to do now is really a Chigger inequalities, which has nothing to do with Ramanujan. It's just if I have the vertex spectrum concentrated and the edge spectrum bounded for below, I get Chigger for linear sets.
So you're basically saying that the number of triangles is q cubed times n for every partition.
Yeah. Okay, so last time we looked at this form. We put here C, A, and B, and we used the fact that we had a complete skeleton, and then we were able to understand this form, and it was Kirchhoff, and it was nice. And then Avi, you said that we need to change this form for the different case, and this is what I tried to do for a long time, to understand how to build a Kirchhoff form for the general case, and I never managed to do it. In the end, we just stick with this form and make the best of it. So this will be our F. Now F is not in Kirchhoff, so let's write it as the exact part plus the Kirchhoff part.
Just to make sure what you're trying to get is to show that evaluating the Laplacian on this f will give a number below your h of epsilon.
Yeah. So it will be a lot. Now I'll start getting errors and move them around, but this is the idea. So this is F, and I still know that this is bounded by the Kirchhoff part. Okay, because this is Kirchhoff and this is Riley quotient for Kirchhoff function. Now, here I don't need this Kirchhoff because this is already in Kirchhoff. So, because of the orthogonal composition, the exact part will be perpendicular. And I also don't really need this kh here because the Laplacian take exact function to 0. So actually here I still have ff. But here I have the Kirchhoff norm, and this is the norm of f minus the exact part. Now last time we did the analysis of this and showed that this is T A B C n square, and it was, and we didn't use complete skeleton there. It was just looking at the differential here, moving this here. No, it's exact.
Oh, I see, okay.
It's just moving the differential here, and then the differential of this form really gives a plus b plus c to all the triangles here and 0 to triangles everywhere else. We didn't use the complete skeleton there. So our goal now is to understand what happens here. And okay, for f actually, for the size of f, it's really, I need to understand how many edges go from A to B, from A to C, from B to C. This is by the expander mixing lemma for graphs. I have linear size graph, then I know I have concentration, so this I can understand from that. Here, now we have we want to show that this is small, so we don't deviate a lot from the norm. And like I said, the idea is still this guy. So now what I want to say is that the lower Laplacian okay, I want to say that this is something like lambda 0 projection plus some error term for the epsilon, where my I didn't, okay. So what we have now is the spectrum of delta 0 is between some lambda 0 minus epsilon, lambda 0 plus epsilon, and the spectrum of delta 1 is at least lambda 1. And so this is this lambda 0. I want to say that, okay, now it's almost the projection times lambda 0, but also I have an error term. So, and it's the same proof. So del 1, the lower Laplacian on the Kirchhoff is still 0. The image is still the exact part. And the spectrum, exactly the same thing, is that the spectrum, except for the 0, is the spectrum of the graph Laplacian expected from the 0. And this is exactly what we said is between lambda 0 minus epsilon, lambda 0 plus epsilon. So it's exactly what we did here, that except that at the end we don't know that it's n. It's concentrated around somewhere. But this tells me that it's the projection onto the exact times lambda fs and some error term of size epsilon. So
trying to compute now is the quadratic form of applying px to f.
So this is the projection onto the exact form of f. It's not me. And I don't need to project also here. And this, because of what happens there, it's 1 over lambda 0. And now the lower Laplacian, so let's already write the boundary of f, boundary of f. We need to understand this. And here again we'll need the expander, the fact that the graph is an expander. So we have this. Now we sum over all the vertices at what happened in the boundary. Now for any vertex, let's say here in C, what do I get? From all these I get, this is B. For all the vertices in B, I get C from any edge coming from A. So let's say I have here some V, the value here, and C going out from here. So the value here is the number of edges going from A to V times C minus the number of edges going from V to B times A. Okay?
But you know what these edges are roughly for a random V.
So the thing is this, if the skeleton was complete, then there would be AC, there would be A edges coming from A to this V, and then it would be AC, and here it would be, V going to C. Yeah. There would be C edges going to C for each of the minus way A, so this would be 0. But here, it's not a complete skeleton, and the thing is I can't really say that these are similar, because this is a single vertex, and for a single vertex everything breaks down. But the idea is that it can't happen that a lot of edges, a lot of vertices in B have much more edges, much more neighbors in A than neighbors in C. This is the basic idea here, and this is how you do this. So let's start with the sum over, let's start with V in A. So let's call them alpha and compute this. So we have the edges from B. Okay, we started with B. What? Yeah, let's start with the. So this is A beta C minus E beta C times A. And this is squared. And now the idea is write this as sigma over all the alpha in A, and then the Kronecker delta for alpha neighbor of B. And the same here, B gamma for all the gamma in C. Then when I square, I need to open these brackets. What I get at the end is here beta, and here it would be alpha and alpha prime. But C square, alpha alpha prime, and then delta alpha neighbor of B, delta alpha prime neighbor of B. This is just from squaring this part. And then 2CA sum over all I want also the beta here. So alpha and gamma. So this would be delta alpha beta, delta gamma beta, and A square beta gamma gamma prime, delta gamma, delta neighbor of gamma, and delta beta neighbor of gamma prime. Okay.
At the end, you just normal projection on the exact. It's constant fraction less than the.
Yes.
If you want to get instead of 1, you just
Instead of 0. Yes.
the projection cannot be big on the. That's all you want.
Yes. So okay, so we translated this. When we open this, it looks more combinatorially. So now this is just C square. So this is actually C square, and then the number of passes going from A to B back to A. Do you see this? We go over all the alphas in A, alpha prime in A, beta in B, and we ask whether it's a path. And minus to BC passes from A to B to C plus A square passes from C to B to C. And now, again, this is again a question about an expander graphs. We understand the number of passes well. And this will be C square, and then this will be lambda square over n square A square B plus some error term, which is, so I have here this C square, and from this I will get something like, I think, lambda square epsilon A square B. And from this guy, I will get minus BC, then lambda square A BC, plus some error term, and the last one is A square, lambda square, and all these cancel out, basically. This is what? 2, yeah.
CA, not CB.
B. Where? This is ABC, and then C square B, A square. No, this is okay, I think. And all these cancel out.
Yeah. That's the main task.
Yeah. So this is basically how to say this. The thing that it can happen that a lot of edges have more than neighbors in A than in B. This is how we make it precise, and we get only these error terms, and they're pretty much okay. And it means that you work everything out, so this is not so bad, and this is not so bad because of the expanding mixing lemma, and this is what we know. So at the end, what we get, I'll just tell you so you get that the number of triangle in ABC over ABC is at least lambda 1, and here we have this lambda 0 minus, I think, some constant over the epsilon. Let's see if I... I'll write the exact thing. It's lambda 1 here, lambda 0 minus epsilon, and here 1 plus 10 and third over ABC. And the thing is that if ABC are a constant fraction bounded by a constant fraction of n, then I can bound this, and the epsilon is the effect of the epsilon is bounded. And this also gives you the one we saw last week, because for a complete skeleton, epsilon is just 0. And we get here n. N squared. We get here n, which cancel this n, and we get what we did there. Okay.
Was it needed to use the fact that the spectrum of delta 1 is bounded?
This is just here. If it's not bounded, I get, if it's 0, then I get that this is positive, but I know it's positive. Right. Yeah, at the end, I want to say that this is bigger than lambda. If it's big, then it'll tell me something.
And this also extends to higher dimensions?
I think so, but this is very recent. I mean, this is something from the last 2 months, and I think all the arguments carry to higher dimension, but I need to sit down and do it.
Thanks.